Welcome to The Explainer. I'm Dr. Chem, and today we are embarking on an incredible journey straight into the nanoscale. I want you to imagine brilliant golden beams of polarized light perfectly striking a highly polished metallic surface. What we're looking at here isn't just a simple reflection. No, we are witnessing the foundational physics of Surface Plasmon Resonance spectroscopy. Over the course of this explainer, we're going to unpack exactly how this awe-inspiring optical phenomenon allows us to watch the invisible, real-time dance of biomolecules. It's truly fascinating stuff.
Okay, let's dive into this. To really understand this technology, we have to start way down at the atomic level, right at the surface of a remarkably thin gold film. As you can see from this beautifully phrased quote, the electrons in gold simply aren't locked down. They actually float freely, acting as a negatively charged sea. So when light hits this metal under very specific, precise conditions, it disturbs these electrons, creating a local charge imbalance. It's a lot like dropping a stone into a perfectly still pond, causing waves of electrons to literally move in perfect unison with the incoming waves of light. And that unified wave, it actually has a name. It's called a Surface Plasmon Polariton, or SPP. Essentially, what's happening is that photons from our incoming polarized light are transferring their energy directly over to the metal's electrons. And this energy transfer creates these incredibly vibrant, glowing, wave-like oscillations, the surface plasmons, that become permanently trapped right there at the interface between the metal and the surrounding liquid medium. Think about that for a second. We are literally trapping light energy as an electron wave right on the surface of the gold. And this brilliantly illustrates exactly what we're talking about. Notice the light coming in through the glass prism from the bottom left, striking that ultra-thin gold film. But look really closely at the interface itself. Do you see that red glowing wave? That represents what we call the evanescent wave, which is physically penetrating into the sample medium just above the gold. The energy has successfully been transferred. And because of this transfer, the light that actually reflects back out, which you can see heading to the bottom right, is missing some of its intensity. A chunk of that light has literally been absorbed by the gold to fuel those oscillating plasmons.
Section 1. Inside the SPR instrument. So now that we understand the absolutely dazzling theoretical physics at play here, let's see how we actually harness this phenomenon inside a real SPR instrument to get actionable scientific data. To make this work, scientists had to figure out how to perfectly couple the light with the metal. Let's compare the two main competing designs. On the left, you've got the auto configuration, which requires a microscopic air gap between the prism and the metal. Now, as you can probably imagine, trying to maintain a flawless, uniform air gap over an entire surface is an absolute nightmare in a practical lab setting. But that brings us to the right side, the Kretschmann configuration. This was a massive game changer for biosensors. By coating the metallic layer directly onto the prism itself, it completely bypassed that notoriously difficult air gap, making the entire system highly sensitive, incredibly robust, and operationally simple. Let's actually walk through the inner workings of this incredible machine. Starting over on the left, we kick things off with a halogen light source. That light passes through a polarizer to align its waves perfectly, and then it enters our glass prism. It strikes the gold-coated sensor chip exactly where our biological sample is flowing through a specialized cell. Now remember that missing light intensity we just talked about? The optical detector, situated at the bottom, captures the reflected light to measure exactly where and at what angle that intensity drop occurs.
Section 2. Mechanics of molecular binding. All right, so we've built the machine, we've excited the electrons, but what are we actually measuring? We are looking at the mechanics of molecular binding, the invisible, nanoscale dance of biology. And here is exactly why SPR is considered one of the most powerful analytical techniques in modern science. It is completely label-free. For decades, if scientists wanted to see if protein A bound to protein B, they had to attach these bulky, fluorescent, or radioactive tags just to make them visible. But tagging a protein is kind of like forcing a dancer to wear a heavy winter coat. It changes their shape and alters how they behave. SPR, on the other hand, allows us to watch these interactions happen in real time, completely in their native state, without any of those costly or disruptive labeling reactions. We're observing nature exactly as it is. And this is how that biological dance actually looks to the machine's detector. You see this really sharp drop in the graph? That is the famous SPR dip. It represents the exact angle where the gold absorbed the light to create our surface plasmons. But here is where the magic happens. When biomolecules bind to that gold surface, they physically change the local refractive index. And when the refractive index changes, the specific angle required to excite those plasmons shifts as well. The detector actively tracks the movement of this shadow. If the shadow moves forward, molecules are binding. If it moves backward, they're breaking apart. It's brilliantly simple, yet incredibly profound. We generally break this interaction down into two distinct phases, glowing on the sensor surface. First up is the association phase. This is where we flow our sample, which we call the analyte, over the surface, and it starts binding to the target. The mass on the surface steadily increases, the refractive index goes up, and that SPR angle shifts. Then we hit the dissociation phase. We stop the flow of the sample and instead wash it with a clean buffer. The molecules naturally start to break apart, the mass decreases, and the angle shifts right back. Section 3. Decoding the SPR sensor bro. Now, all of those tiny microscopic shifts of light and shadow are completely meaningless unless we can actually translate them into tangible, actionable data. And that's what you're seeing right here. The system continuously plots that shifting SPR angle over time to dynamically form these elegant curves, called sensograms. The vertical axis is measured in response units, or RU. To put that into perspective, just one single RU represents a shift of 1/1,000,000th in the refractive index. It's unbelievably precise. So as the curve sweeps upward, that's our association. When it levels out at the top, equilibrium is reached. And as it swoops gracefully back down, that's dissociation. From those elegant curves, the computer extracts some seriously precise math. We can calculate K, which tells us exactly how fast the two molecules snap together. We calculate KD, telling us precisely how fast they fall apart. And by simply dividing those two, we get KD, the equilibrium dissociation constant. This is the ultimate big picture measure of overall binding affinity. Is it a strong, tight bond or a loose, weak one? The data here gives us the complete fingerprint of a molecular relationship. Now, scientists generally have two primary ways to extract this affinity data. Kinetic analysis is the absolute gold standard. It fits mathematical models to the entire sweeping curve, capturing both the on and off rates simultaneously. But sometimes you run into molecules that bind and break apart incredibly quickly. In those instances, we shift to steady state analysis, which just looks at that flat plateau where the interaction reaches true equilibrium. Knowing when to choose the right analysis is absolutely key to getting accurate, reliable data. Section 4. Troubleshooting the nanoscale. Of course, bringing this theoretical physics into laboratory realities comes with a few headaches. When you're detecting protein amounts so tiny they're sub-femtomolar, which is almost unimaginable, even the slightest environmental factor can completely ruin your data. If your baseline signal starts drifting, it could be something as simple as a microscopic air bubble. To fix this, scientists have to meticulously degas their buffer liquids. If the signal looks noisy and jittery, you might be dealing with tiny room temperature fluctuations or even electrical noise from improper grounding. So flawlessly stabilizing the environment is absolutely critical to preserving the integrity of that delicate optical signal. Another really major hurdle scientists face is nonspecific binding. This is basically when the wrong molecules stick to your sensor surface like uninvited party crashers. It totally ruins the invisible dance we're trying to observe. To manage this, scientists follow a rigorous set of procedures. First, they'll chemically block the empty, unused spaces on the sensor with substances like BSA or ethanolamine to prevent rogue sticking. Then, they painstakingly optimize the pH and the ionic strength of their buffers. This ensures that only the intended target binds, and that absolutely everything is washed away cleanly during regeneration. It requires a tremendous amount of precision.
Section 5. Real-world biomedical applications.
We've looked at the physics, we've explored the machine, and we've decoded the data. Now let's step away from the lab bench and look at the massive global healthcare impact. Because make no mistake, this isn't just a fun academic exercise. This technology is actively saving lives. SPR is used heavily in biotechnology facilities worldwide. It's an absolutely critical tool for developing new vaccines and characterizing exactly how well our antibodies fight off viral threats. Major pharmaceutical companies rely on it to discover how new drugs interact with target cells. And even more amazingly, SPR is being deployed right now in clinical diagnostics to detect minute protein biomarkers in human blood serum, paving the way for the early detection of devastating conditions like pancreatic cancer, ovarian cancer, and coronary artery disease.
So, the crucial point to take away from all of this is that these tiny, microscopic graphical shifts, these little micro adjustments in an angle of reflected light, they represent monumental biomedical breakthroughs. By simply interrogating the phase and intensity of light as it hits a gold film, we are successfully tracking and mapping the immensely complex, interconnected molecular networks that make up human biology itself.
And that brings us to the bleeding edge of the frontier. With the unprecedented ability to watch the fundamental building blocks of life interact in real time, completely unhindered and in their native states, it really begs the question, what invisible interactions will we illuminate next? The future of biomedical innovation is truly boundless. Thank you so much for joining me on this explainer. Until next time, keep questioning the invisible.